Hi, hello. Welcome to the presentation in the steer track of Colocation.Green. Happy to be invited. My name is Carl. Hi, great to meet you. Thanks again for steer, and especially Mohan and Max and Lasse for inviting me to talk about our data center project, soon to be data center site. I'm excited to show our progress and our technologies on how to fight CO2 emissions, reuse energy, and create circular systems in the data center world. Okay, let's jump into the presentation, shall we? Perfect. You can see me, and you can see the start of the presentation. We will circle back to this picture quite a little bit later, but basically this is where we want to deploy our modular data centers. This is the science topic, integrated energy, the future of HPC. Just wanted to show here our exactly data center location that is ready with foundations to be equipped with data center modules, and also we'll come back to the data center modules in a bit. There's just a bit of an impression about our location and the task we need to do to get it up and running. What I'm going to talk about especially is very briefly a bit about me, how I got here, why I'm talking to you. Then start with the why. How do we get into the necessity building sustainable data centers, and why are we doing it in the region where we're doing it, and how to actually measure CO2 in the data center, what's going into it, how we enable sustainable HPC, how do we recover the heat, and what is actually then possibly happening to those with that energy. So let's get started. So besides the initial introduction of Carl, 36 years old, married with two kids. I have an engineering degree, I have a business degree, plenty of qualifications that come in handy left and right when dealing with complexity and complex architectures like data centers. Although I am an absolutely self-taught data center operator in a sense. I founded a couple of companies and initiatives on that topic. We started out in 2015 with WindCloud Brother, where we had perfect setting, we had battery storage, we had biogas plants, we had a nice wind farm. But what we were lacking was the ability to actually have a legal construct to use wind energy directly. Because of that, we founded another company, WindCloud 4.0, which is still operating. You can check them out under here, which has a bit different strategy. Potentially also want to be sustainable, but they go with an island grid, so they want to be totally self-sustainable on a former NATO bunker location, and they use existing NATO bunkers to build up their data centers. At the moment, they have a nice demonstrator where they use algaes for binding CO2. It looks very good. And now, so since 2020, we are now pushing Colocation.Green. Feel free to check out the webpage, where the main differentiator between the WindCloud 4.0 and WindCloud Brother is that we actually have the foundation as the direct access to wind energy within a wind farm. We put our IT directly to the wind farm. So what changed over the years? So the energy emissions and the energy price was going down. Both were going down. This is why it's the green era. With more experience, we got a better grip and better handle on how to improve our energy track, and definitely what decreased is the crappiness of our DC infrastructure. Whilst we had in WindCloud, we actually were building out our own shipping container, manufacturing together with a specialist for farming equipment farming equipment ventilation to get the heat out. I'm too ashamed to show you that first prototype. But what is very important to notice is it taught us immensely important lessons on what is actually important in a data center, how to operate it, and what temperatures and fluctuation in temperatures servers actually can deal with. Because there was a massive discrepancy between how much energy was actually put into cooling servers back into 2015 when we started, and still is up to this date. Is immensely amounts of data is wasted. Cooling servers that basically do not need cooling, maximum need ventilation. Well, in WindCloud we were actually having a very nice data centers to start with. Nice data center room was small, but we upgraded with all the necessary UPSs, upgraded cooling, upgraded connectivity, made it redundant, got it certified, and started, selling out proper colocation and cloud services at WindCloud and Colocation.Green. We take all those lessons learned before and just create the most sustainable and most cost-effective data center infrastructure in Germany. Underlying idea did not change that much over time. Get the wind energy directly and make it sustainable and competitive. Okay. How do we got there? What's the big thing we're taking? What's the why? All numbers basically point in one direction, that we have an immense problem in the CO2 emissions created due to the operation of IT equipment and the production, as well as the e-waste. All the servers are phased out after 5 to 7 years, creating a massive growth of actually e-waste. That is, a lot of that is not recyclable, which is turning into more and more of a bigger problem. Alongside with the mineral of mining of those special ingredients you need to actually create chips and servers and storage. And all the buzzwords you hear, IoT, industrial IoT, here is AI, mining, big data, everything, every buzzword more, even every technology more, leads to an actual increase in demand for data centers and to an increase in global electricity consumed. And 10% in 2025 is quite a big number. I have another graph demonstrating this a little bit later, but all those point into one direction, that is massively increasing. And we're facing now a crisis in society, a crisis in the economy due to Corona, and obviously beforehand and ongoing is the crisis in climate. And we need to get a grip on digital products to get a turnaround in the energy shift and do not increase CO2 spending for digital and data center infrastructure. This is just, just a more visual representation of all the numbers beforehand. Just there was a prediction that AI will increase this to 10%. To be honest, the most recent research I know is that the number is at the moment in 2020s somewhere towards the upper number of this, and nearly all of those graphs go exponentially. And that is a big issue, especially since we are already here in 2020, towards the end of the graph, where it's going into massive growth. Just imagine at the moment most of the data created is human-based, and IoT means that from now on devices to device communication will grow, and that data will also be stored and processed. So very soon all that data created by machines is exceeding our data created, and there's quite a massive issue. So how do we measure CO2? Basically, it was divided up into 3 scopes. I took this example from the Green Web Foundation. Check out the link. It's quite interesting what those guys are doing and how they try to tackle carbon emissions. Scope 1 for companies: what fossil fuels are you actually burning directly? Scope 2 is what emissions are created from energy usage. So this is created through the medium of coffee creation. And scope 3 is what is nowadays discussed heavily, is the supply chains and the total social responsibility and also CO2 intensity of the supply chains. So how does it actually look like in a data center? Jump into scope 2, because that was our main driver, in WinCloud 1 and 2, was actually making this sustainable through the energy used. This basically solved, we can use wind energy and have very, very little emissions. I come to a calculation example later. Scope 1 in a data center, what emissions are actually created directly in a data center, is the running of backup generators. This is not immensely much, but it's still noticeable. And scope 3 would be the emissions from the supply chain, sourcing of servers, construction of the data center, travel, everything else that is indirect, the indirect emissions associated with this. The servers, for ourselves, since we are a colocation provider, not a cloud provider, is something that we excluded, in our example. But actually, if you are running an application and if you run it on hardware, the servers make up to 76% of all CO2 emitted running any workload. So this is obviously a big issue, and we have already also have a way to fix this, but it's not topic of my talk today, but feel free to contact me later. So, what's our solution plan out? How do we do it? What's the way? This is a very quick analysis of our CO2 emissions. So running the generator every month accounts for about 1 gram for all kilowatt hours consumed in our data centers. The combined usage of wind energy and the energy we get from the grid for about the 5% where there's no wind time of the year results into for up to 22 grams per kilowatt hour consumed in the data center. And scope 3, the construction of the data center, where we also work with a lot of lean technologies, data center technologies, to reduce this, accounts for a lifespan of 15 years for the data center, for around 5 grams per kilowatt hour used in our data center. This is something we're still working out and trying to get more precise, but for now this is a fair estimation of what we're doing. So overall, although we run very efficient data centers, although we use wind energy, we still are not carbon neutral. That is a very important fact to notice. We still are emitting carbon emissions. But compared to the German average of the energy mix, we creating massive savings. So bringing your workload to us will result in immediately in savings for your CO2 emissions, for your CO2 bill. And to bring it one step further, how do we then go about and make it actually carbon neutral or even carbon positive? Is the data center solutions I'm talking today are warm water cooled HPC clusters, which we'll see in a minute, and they actually have the potential and the feasibility of reusing the heat that we create in the data center. Those are water-cooled solutions. The heat energy is directly bound in the water and can be reused easily and for a wider range of purposes instead of just air cooling our servers. And this is the number I got from a befriended data center operator who's drying wood chips with his data centers, and he guesses or estimates that he saves 46.5 grams per kilowatt hour when drying those wood chips. Since we actually can use 70% of our electrical energy invested, with that factor we have resulted savings for each kilowatt hour that we use of 32.55 grams. Subtracting this from the 28 grams that we actually have in our CO2 emissions, we become not only carbon neutral but slightly carbon positive. That is, if you will, the whole trick, that by generating renewable heat, we actually can free us from emissions and become carbon positive. And that is our biggest goal, to become carbon positive and stay carbon positive throughout our operations for those HPC use cases. Why do we do colocation? Why is this a business model for us in the data center world? Gartner, very simple, Gartner predicts that we are from today 10%. We are going to enterprises closing down their existing data centers to 80% in 2025. And I just recently got this confirmed by big OEM server manufacturers that a lot of big companies are moving into specialized facilities or to the cloud. And us being the one with the most cost-effective data centers and energy cost, plus saving a lot of CO2, we want a fair share of this. Why do we have to be so forward-thinking and so aggressive with our technologies and our solutions? We are in the north of Germany, just here at the coast. But the main hub of data center usage is Frankfurt, which is just around here. But if you see, just 30 kilometers for us is the Danish border. From there on starts basically the Nordics territory, as we like to call it, or I like to call it the 5% region, which offers sustainable, cheap energy just below 5 euro cents nearly throughout all this region, which is immensely successful in attracting data center solutions. And we just want to be able to hold some of those projects within Germany. especially since there are many HPC projects. A lot of them require very high data security levels, and some, like big data projects where you have, critical user data, sensitive data that have to stay in Germany, we are able to guarantee, all those by the German law, by just being still in Germany. Okay, coming back to the actual site, as you've seen from the picture, we have a lot of wind energy. Here you see 3 of our actual wind energy turbines, 3.45 megawatts each. We have currently 86 of those. I think end of next year there will be 90 turbines, then with a maximum capacity of 300 megawatts, because a lot of them are repowered currently. This is the switchyard, which has 4 big transformers, which is transforming the energy from the wind turbine from 20 kilowatts to 110 kilowatts. I'll have a slide on this in a second. This is the actual data center site, which was not initially designed for the purpose of using data centers. It was created to deploy battery storage, but the cost of connecting the battery storage to the grid was so expensive that the wind park stopped that and created their own grid. This is basically the whole trick on how we can have the lowest energy cost in Germany by having a wind farm that is also running their own grid. Some very important side notes. I am actually, this shot is nice because it's actually looking at my home where I was raised. So I've come a long way just to now be able to deploy data centers just in the neighborhood of where I was growing up. More importantly, over here are pig farms, biogas plants, and crop dryer or cereal dryer, which definitely require the use of heat. So there's even an existing heat grid here that is still looked into to be extended, and we are in a perfect position in creating more and more heat for those use cases. How's the actual energy setting set up? How does it look like? As I said, this is our wind turbine. It produces energy on the 220 kilovolt voltage level, and all those nearly 90 turbines are feeding this into the central switchyard, which you just saw on the picture earlier. The switchyard has 4 big transformers, and they are in a redundant setup so that they can be switched over, and all the energy is transformed to the 110 kilowatt voltage level, and then fed into 2 separate directions, so into redundant other switchyards into the electric grid, where it's then transported and used, hopefully in Hamburg and beyond, which is a big issue. This is why we want to use it directly. We connect our data center directly on the 20 kilowatt volt level, and because of the amount of energy we actually want to use, we take the energy in the same level directly created from the wind turbine. This is obviously simplified, but basically the data center site in Germany is connected and backed by 3 different grids, and that is quite a unique setting, especially having 200 separate 110 kilowatt grids connected to your switchyard, which enable us to grow well beyond our initial data center data center stage. You saw the picture earlier. This is a schematic image of how we actually plan to utilize those foundations. So we're gonna start with traditional business modules, 5 kilowatts per X, nothing too exciting. All the certificates, very redundant, very efficient operation. I have a picture on this earlier. The HPC module that is direct-to-chip water-cooled, which is something I'm going to talk about in a bit more detail. And the another specialized module, OCP, or air-cooled HPC, up to 20 kilowatts per rack, with a focus on air-cooled high-density workloads. And we have another exciting technology planned, which will be an immersion-cooled module. Immersion means that servers are running in big tanks full of oil, and I have some details on this a bit later. Total numbers, starting capacity for 2021, 20.5 megawatts in installed capacity, and PoE of the overall site of only under 1.05. This is our business module. 2 modules, 18 meters long, 4 meters wide, 3.5 meters high. We have a redundant UPS system. Each of those is well dimensioned to feed into both of the white spaces, so that we have the 2N supply ensured. The cooling of the technical facilities is also handled by the big coolers on top of this data center, which you see in another picture, and the necessary cooling air is pushed over here into this by ventilation. Here is a little bit of a pre-room, because it's windy and rainy where we are, so it's a bit nicer just not to directly access the data center from the outside world. This will be having 40 racks, so an overall capacity of IT is what we estimate, or we configured it for 200 kilowatts. This is the OCP module. This is the cooling equipment that I was talking about. This is an indirect free cooling. It's the technical terms. Basically what it means is that you take the air, move it through this heat exchanger. It's an air-to-air heat exchanger, and then there is the outside air going through, coming in cold, coming out hot here, and that you have the cold air created, brought in front of the servers, moving through the servers, creating warm air that is raised or sucked in on the back of those cooling units, and then the circle starts all over again. This has fewer racks but a higher installed capacity due to having higher density. Since the OCP technology, this is a specialized standard of data center and data center operation, which is which was created by Facebook and joined by a lot of others, which has wider racks and generally higher workloads and higher density requirements, which is not so easily to integrate into an existing data center design. Hence we created our own module for this. So now coming to the HPC modules, those are the ones that are actually cooling with water or liquids, other liquids, which ensures that the heat that is generated is transferable, transformable, and can actually be used. So I've highlighted those two models: the HPC module, set direct chip, and the immersion cooled module, which we are getting both into now. So this is the HPC module. You see, we still have an air-cooled system on top. This is just due to the fact that although the direct-to-chip water cooling is allowing for a lot of energy to be directly transferred away from the chip, there is still not all of the energy can be moved directly into the water. So we have about 20% still that needs to be moved over, moved away over the air circle, with nearly 1 megawatt capacity installed. So that still results in about 200 kilowatts. So there's still a lot of air cooling going on in this configuration. The water cooling, the water circle itself is moved out, then it goes to these rear cool units, and they cool the warm water cooling down. This is the immersed cooling system. We have not finalized the design for the module yet, since this is the reason why I'm showing basically the submer. This takes from submer, the submer data center minimal setup, and this helps to understand what this is doing. You see here two high available redundant pumps. You see again the back cooling units to cool off the heat, but this does not look like the standard rack. Those under those flaps, you have an oil base where you put in the servers, not traditionally in your rack. You just push them in on top of each other. Here you have a tank, and you put the servers in one after another, but you just from top to bottom, not from front to back. This oil base has their own heat exchangers, and gives the oil gives through the heat exchanger gives the energy to the water circle, and the water is then run hot into the back into the cooling unit and moved back through the pump cold again into the tank, and the circle continues, and it allows you, what's exciting about this, it allows for also very high density, but also of very high water temperatures of up to 70 degrees, which is the starting temperature for example for a heat grid, which luckily we have access to heat grids, but this is very is the lowest useful temperature to put it into a heat grid or to use it for process energy, and all the temperatures below that need transforming by some form or another. So you need to spend extra energy to create temperatures that are actually usable. So this is a bit of a problem. Okay. This is the HPC view from top. So we're looking at 20 racks, of which 4 are HPC storage, very specialized and expensive and fast storage. And then in clusters of 4 racks are the compute racks, which make of 85% of the capacity installed in terms of energy consumption and heat generation. And those are connected via piping to the central distribution unit, which has a heat exchanger to itself. So there's a circle here, which we'll look in detail in a bit. And after it runs through the heat exchanger, the heat goes out to the cooling units. And you have another pump setup here. This is the one that is then, if the energy is demanded by the heat grid or by the commercial area or other processes that require heat, this setup reroutes the circle from just cooling off into the air, reroutes it to be fully used. Hence we create our carbon savings. Unfortunately, the HPC module only has a maximum temperature of about 60 degrees, so that is a bit lower. This is our water cooling setup in just a schematic view. We just looked into the module. You'll see here an HPC rack which has manual valves, having one in and one out. Cold air coming through here, going into the rack. We'll look into the detail of this on the next slide. The warm air is going out over this valve through here, and with a return of 62 degrees it goes in the heat exchanger, and the heat exchanger goes in with his hot side into his cooling circle over the cooling unit, comes back with about, through the pumps and the manual valves, of about 45 degrees, and goes into the server again with 50 degrees. So this is a warm water cooling setup. And after the heat exchanger, basically here is the drain valve or filling valve. There could be another valve to reroute the energy for our repurposing of heat. Concrete uses community heat grid. This is existing. We only need to build a few hundred meters to connect to it and pump our heat energy towards the community that's also running the wind farm. The area around the switchyard is becoming a commercial area, so we will be able to supply other businesses with heat, and they also have the freedom to get the cheap energy of the wind farm. So this will be becoming a very attractive new commercial area in Germany to place a company. And obviously, as you've seen around, this was a very rural area, and so farmers are very innovative. If you give them something for free, they will be able to do something with it. So there's a lot of process heat for greenhouses, and we are very certain that somebody will find a way to use those as soon as we are able to supply it to them. How does it look in detail? How does a specific water-cooled server look like? So you have cold water in, hot water out. This is distributed over this panel into the different nodes. You have a two-socket server here with two CPUs and RAM sticks to the left and right. All those are water cooled, so the energy of the RAM and the CPU and even some smaller part here, this all goes into the water and is cooled off directly. Things like the efficiency of the energy connector and those things, those still are creating the leftover energy that is then cooled off via the air. But the majority of energy that is used and created heat is cooled directly via the chip. Is going over the CPUs and then back into the warm water circuit. Those servers are stacked on top of each other and are in this form of chassis. You have a special connector that is connecting to 6 separate servers, as you can see here, and in this configuration you have 6 of those 6 times 6 is 36 servers on top of each other, which all are connected to this 6-drop manifold, which then is connecting into the warm and cold water cooling circuit. So just let me look over the features quite quickly if I forgot to tell you anything. Obviously, yeah, our site will be monitored 24/7. We have a partner companies who are already running a lot of critical infrastructure who has a critical network operations center that you need to run your data centers. And we partly manufacture those modules ourselves, so we have the flexibility to go in a lot of different directions. Features of how much energy actually can be equipped in such a rack is up to 150 kilowatts per rack can be installed in our modules. We are flexible in the usage of 19-inch, 21-inch racks and immersion cools. We also enable rear door cooling in special modules that we have, and we will also create special modules for you if this is necessary with ourselves or a partner. And just to let me look over this business colocation. So we are preparing quite a lot of certifications. Some of them are already enabled and active, and we have a massive team to support you with your business and IT needs. And running IT infrastructure is well, we had a lot of experience in this experience that we built out actually in the prior companies of WindCloud. So to bring this home, we believe that by combining renewable energy with very efficient data center design and operations, we will have the best profitability and sustainability of all German data centers. We focus on reducing CO2 emissions and creating very competitive solutions for you. And with that, I would like to thank you. If you have any further questions, feel free to ask me, and I'm happy to go into this discussion after this talk. Thank you very much. Bye-bye, Carl.